Welcome to the second video in this series of special relativity in the Pauli algebra of space. This is a geometric algebra approach to special relativity, which I think is pretty useful. In this video, I will be going over differences between frames and then the Lorentz rotors. So in the algebra of physical space, there are things called rotors. So in GA in general, but in the algebra of physical space, there exist things called rotors. These are defined as exponentials of the negative 1/2 and some bivector, and then t. Then the initial rotor, where, just for emphasis, you have that B is an element of the algebra, but it's a bivector, so it's in the grade 2. And also in the APS, also within the APS, there exist things called boosts. You could also call this a hyperbolic rotor. So if you call this a hyperbolic rotor, you would call this a Euclidean rotor. But we're just going to call these boosts these rotors. And these boosts generate hyperbolic rotations. E to the negative 1/2, and then defined phi. Phi is the hyperbolic angle, and then it's in the direction of motion, and then times t. And then there's if there's an initial, then of course you have v hat is an element of the vector space, the vector subspace of the algebra of physical space. Now these transform objects and therefore create different frames of reference. For Euclidean motion, we have body frame and world frame, and then we have lab frame and rest frame for hyperbolic motion. Now for vectors, or yeah, so for what do you call it? For rotors, I'll just specify Euclidean. You have what's called the body. You have the orthonormal fixed frame. So I'll call this you have two things. Orthonormal fixed frame. So this frame is fixed in space as a whole, EJ. And this is called the world frame. Similarly, the rotating frame has an orthonormal frame, but it's not fixed with respect to the world. So you end up with something called, or you get the orthonormal rotating frame. And this is called the body frame. The relation between these two is given just by the rotor. So you have that f jth component, or the jth vector rather, is r e j r dagger. Where if you're familiar with geometric algebra, this is just the formula for rotations in any dimensions. So therefore, it holds in the algebra of physical space as well. But how do you visualize this? Well, I have drawings, so that's good. Let's move these up. And just put them right here. I'll put them a little lower just so that it's not too visually messy. So in the world frame, you have the orthonormal fixed basis. This is just 2 dimensions. I didn't draw the third axis because it's just another thing to draw. But the way it works in 2 dimensions is the same way it works in 3 dimensions. So you have the orthonormal frame E1, E2. That is your world frame. So this is where you'd be in the world. And then as you're rotating, the world frame sees F1 and F2. I drew these as smaller, but they're supposed to be vectors of the same length. I just drew these as smaller to emphasize that we're in the world frame in this picture, observing the body frame. So as it moves, as it rotates. But if you transform into the body frame, which you can, so if you were to transform into the body frame, you would end up with this R dagger F J R. Then the transformation into the body frame then puts the F1 and F2 as the main coordinates, and then you're observing the world, the people, or like being in the body frame, you observe things in the world moving. And so they're equivalent frame, or they're not equivalent frames, but they describe the equivalent motion, but just from 2 different frames. One being the world frame, one being the body frame. Now, before we get into lab frame and rest frame of special relativity, we need to talk about paravectors. So, in special relativity, we use 4 vectors. And a 4 vector would be given by, some vector has some time component of the vector, some x component, some y component, and some z component of a vector. Well, within the APS, the equivalent is a paravector. That is, a paravector is an object A that is an element of the scalar and the vector subspace of the algebra, and then such that the paravector A is equal to AT component sigma t plus the A x component sigma x plus a y component sigma y plus the AZ component sigma z. This is often just rewritten as AT sigma t, and you can, as I said before in my last video, sigma t is the same thing as 1, so you can forego writing the sigma t here for the sake of brevity. And so you can just say that it's AT plus the vector part of A. And this is a paravector. Well, in special relativity, we know that, in special relativity, or the, what do you call it? The invariant magnitude of a 4 vector is, you have the definition of A squared, which I will just denote A squared, AT squared, minus AX squared, minus AY squared, minus AZ squared. So how do we have this in the algebra of physical space? Well, it turns out there's a way already encoded into the mathematics of this space, and that is to say that in the APS, you define for a paravector, so I'll say this, define for a paravector for A in G0, 1, 3, you find that the magnitude of A squared, which I will just, for brevity, call A squared by itself, is equal to A times its Clifford conjugate, which is equal to its Clifford conjugate times itself. And this ends up being a scalar. So you end up with a real number, ax squared minus ay squared minus az squared. Now, I'm not going to go through the proof here, but I do recommend you go through the proof yourself and see how, when you take the Clifford conjugate here, you end up with AT sigma t, or for brevity, AT plus the vector component of A. And then when you take the Clifford conjugate of this whole thing, so it'll be like this, and the Clifford conjugate will go in, or I'll write it like this, AT plus A1. Well, the Clifford conjugate affects vectors by negating the sign. So you just end up with this. And then if you expand this out, you end up with AT squared minus A1 squared. Now, I said I wouldn't prove that this isn't this, but if you know your definition of a vector squared with itself, then you should get this. And you can do that on your own paper. But that is how the invariant magnitude of a 4-vector is encoded within paravectors. Now this is obeying a metric called the Minkowski metric, where you have a positive sign, a minus sign, a minus sign, and a minus sign. The positive sign is held by the time component of the paravector, and the negative signs are held by the spatial components. And again, if you haven't encountered this, this is called the Minkowski metric. All right, so now we can define rest frames and lab frames. So a paravector in its own, so its proper rest frame, so a paravector in its proper rest frame is given by a rest frame is equal to a rest frame scalar. That is, when a paravector is in its own rest frame, it is a completely scalar quantity, meaning that it only has a time component. It's not moving through space, it is just moving through time. It is at rest. So a paravector can also be related to any co-moving inertial frame. A paravector is related to any co-moving inertial frame. And this is called a lab frame. And just for emphasis, I'll rewrite this also in print. Anyway, and it's related to any co-moving inertial frame by a boost. So that you have A is equal to H, which is a boost. You have the rest frame value, H, dagger. And that is how a paravector transforms under a boost. And you can notice that this definition of how a paravector moves is very similar to how a vector moves under a rotor. That is because they are essentially equivalent. A boost is just a rotation through hyperbolic space. Now, how exactly does this work? What does this look like? We have pictures for the world frame and for the body frame, but what about the lab frame and rest frame? Well, I have pictures for these as well. In an object's rest frame, it is only moving through time. So it's moving through the CT right here. It's not moving in space. It has no velocity. It is just stuck in time. But there's some lab frame that if this isn't moving, then the lab frame is moving away from it. It's co-moving. So say that the object is, or that you want to transform into the lab frame so that the lab will be at rest and the object will be moving, then that's called the lab frame, and that's here where this object, this line right here, is slid from being here to here. And this lab frame right here, which was originally here, is rotated hyperbolically to be at rest. And you can see that they still have the same hyperbolic angle phi between them. So one thing of note, actually, I didn't define this back up here, but the hyperbolic angle phi is defined as the inverse tangent, so hyperbolic tangent, of the velocity over c. And that is the hyperbolic angle here. That is what this hyperbolic angle is. So you can see that in reality, special relativity is just a geometry. It's just a geometry problem, just like some frame rotating. So that's what we will be looking at in this series. We will basically be observing the behavior or modeling rather special relativity using these methods in geometric algebra. But one thing to note just before we move on is that in general there are Lorentz transformations. So in general there exist things called Lorentz transformations. And these Lorentz transformations are defined as lambda equals e to the negative 1/2 omega t, and then there's an initial Lorentz rotor. So this is called a Lorentz rotor or a Lorentz transformation. And in this definition, you see that, or it is seen that omega is equal to phi v plus b. So there is both a rotational component and a boost component. So in general, this is equal to there is a hyperbolic component and then a rotational component, but these do not commute. So this is not equal to RH. And this comes from the fact that this, which rotates the orthonormal frames, when you transform an orthonormal frame through a hyperbolic rotation, that frame is no longer orthonormal. And so because of that, it matters the order which this is taken care of. And so that means that this omega up here, or this omega, is not equal to b plus phi v hat. So in general, the addition here does not commute because the multiplication here doesn't commute. So in general, there are these Lorentz transformations, and a paravector will transform A equals capital lambda A rest, capital lambda dagger. This will be how a paravector transforms, which is equivalent to this right here is equivalent to this, except it has the rotational component here as well. And that becomes extremely important in electromagnetism. As a little sneak peek, maybe just look at the notation from last week or last episode, and then think about this for a second and see maybe how this could tie into that. That's a little sneak peek for what's to come. But yeah, I'll see you in the next video.